Hello, this is mathjazz from Almost Cool. I have here a list of finite math practice problems for my students in my summer class. So, uh, without any further, we'll be doing some problems about set theory, probability, and we'll use these sets for all of our problems in this video. So, our universe, this video, is all natural numbers from 1 to 10. And sets A, B, C, D, E are as defined. We'll use these for all of our problems for the entire video. Okay, so the first set of problems, we're going to indicate, we're going to be given two sets for each problem, and we're supposed to determine is the first set a subset, a proper subset, or not a subset of the second set. So here are pairs of sets. So for example, in question 1, we want to figure out is A a subset of B, or is it a proper subset of B, or is it not a subset of B? Subset means that all of the elements of A are contained in B. So we look at our set here, and for example, 2 is an element of A and not an element of B. So we're neither a subset nor are we a proper subset. So this means that A is not a subset of B. And this is the symbol for A not being a subset of B. So this is read as A is not a subset of B. And we're going to go through all of these. If you want to test yourself, you can do these on your own. Just pause the video and hit play when you're ready to hear the answers. So, number 2, is C a subset of D? So, the element 2 is a subset of, is an element of C, but not an element of B. So, that means that C cannot be a subset of B. So, C is not a subset of D. Oh, I was looking at the wrong sets. C is not a subset of B, but it's also not a subset of D. Same reason. 2 is not in D, so C cannot be a subset of D. Okay, so is the empty set a subset of E? The answer is yes. The empty set has no elements. So that means that there are no elements of this empty set that are not in E. Every element of the empty set, which there are none of them, is in E. So not only this, but the empty set is a proper subset of E because the difference between a subset and a proper subset is that a proper subset definitely does not contain all of the elements of the set that it's in. So for example, all of these sets A, B, C, D, and E are proper subsets of U because there are elements of U that are not in each of them. So A is not a proper, A is a proper subset of U because A does not contain all of the elements of U. So most subsets are proper subsets, but every set is a subset of itself. It's just not a proper one because it contains all of its own elements. So in this case, the empty set is a proper subset of E, and subset symbol, this sideways U, means that the empty set is a subset of E, and the line with a slash through it means that it's not equal to E. So it is contained in E, but is not all of E. And that's the definition of a proper subset, is that a subset is a proper subset if it's not the entire set that it's contained in. So, question 4, we have A and U. Of course, A is a proper subset of U because, for example, well, all of the elements of A are in U, and there is at least one element of U that is not in A, namely 1 is in U, but not A. So are, 3, 5, 6, 8, and 10, but all you need is to miss 1, and that makes you a proper subset instead of what's called the improper subset, which is just the set itself. Number 5, the empty set and U. Well, for the same reason that the empty set is a subset of E, the empty set is a subset of U. And it is proper because there are elements in U that are not in the empty set, namely all of the elements of U are not in the empty set, because the empty set has no elements. 6. Is E a subset of the empty set? The answer is no. E is not a subset of the empty set, because the empty set has no elements, and E has 2 elements, so E has elements that are not in the empty set, namely 3 and 10, so E is not a subset of the empty set. Okay, D and B. So D contains 6, and B contains 1, 3, 5, 6, and 10. So D is a subset of B, and it is proper. So we'll use our subset with the little slash through it. So 8. The set 3, 10, is that a subset of E? Yes. 3, 10 is a subset of E because both elements in the set are in E, and since every element of E is in this subset, this is actually not a proper subset. This is the improper subset, namely the set itself. And number 9, the set of elements X such that X is an element of A and X is an element of C. That's a fancy way of writing the intersection of A and C. In fact, this is usually how you define the intersection, is using this set builder notation here. And so, are all of the elements of this set here in A? Of course they are, because we defined this set to be the intersection of A and C, so all of the elements have to be in A. So this is, of course, a subset of A. Further, when we look at our set A here and our set C here, every element in A, 2, 4, 7, and 9, is in C, 2, 4, 7, and 9. So that means that not only is every element of this set in A, but every element of A is in this set. So this is also the improper subset. So it's a subset, but it's also equal to A. X such that X is in A and X is in C is equal to A, because A happens to be contained in C. So rewriting these, we say that 310 is equal to E, and X such that X is in A and X is in C is equal to A. Okay, so for the next set of questions, we'll be given expressions using basic set operations, and we will we'll write out the elements of the constructed set explicitly. So here are the expressions that we will explicitly write out. So the elements of A union B, well, we take all of the elements that are in A, 2, 4, 7, and 9, and all of the elements in B, 1, 3, 5, 6, and 10, and we get the set 1, 2, 3, 4, 5, 6, 7, 9, and 10. Basically everything but 8. 8 isn't in either set. C intersect D, well, all of the elements that are in C that are in D, well, D only contains 6, and C does not contain 6, so C intersect D is the empty set. We have the set B, leave out E, or B minus E. So we take all of the elements of B, we delete the ones that happen to be in E, we end up with just 1, 5, and 6. We're going to switch these letters around now for number 4 to E minus B. So all of the elements of E, and then delete the ones that happen to be in B. Well, that's empty, because 3 and 10 are the elements of E, and both of those are elements of B, so both of those get deleted. We don't care about the 1, 5, and 6. Since 1, 5, and 6 weren't in E, we can't delete them from E, so we just leave them alone. We want to write out the elements of C complement. So since 1, 2, 4, 7, 8, and 9 are the elements of C, the ones that are not in C are 3, 5, 6, and 10. So C complement is written there. And now we want E complement intersect B. So that's all the stuff that is not in E, but is also in B. So the things that are not in E are 1, 2, 4, 5, 6, 7, 8, and 9. We say, well, what of those are also in B? Well, 1 is, and 5 is, and 6 is. So we get the set 1, 5, 6. And that looks exactly like the set from problem 3. And if we wanted to, we could prove that this always works for set minus and intersection with a complement. That is, if you have two sets, let's call them set A and set B, A minus B is always equal to A intersect B complement. Let's maybe make sure I said that right. A minus B is always equal to A intersect B complement. That's right. So we could prove that these things are always equal. E set minus E is always equal to E prime intersect B. But in this case, we're just proving it for the specific choice of B and E in this specific universe. Okay, so the next problems we'll work on, we'll calculate probabilities of subsets of U. So, here are the probabilities we'll calculate. First up is the probability of A. So, we remember that the definition of probability is the number of elements in set A divided by the number of elements in our sample space, which is this universe U. So that means that probability of A is equal to the number of elements in A over the number of elements in U, which is equal to 4 elements in A divided by 10 elements in U, which is equal to 2/5. So the next thing we want to calculate is the probability of B union C. That'll be the probability of B union C over, sorry, the number of elements in B union C over the number of elements in U, which is 10. And I'll just write 10 for the rest of the problems. Well, how many elements are in B or B or C? Well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So all of them are in B union C. So we have that the probability of B union C is 10 over 10, which is 1. So no matter what number you're picking out of U, it will either be in B, or it will be in C, or it'll be in both. Probability of A intersect B is the probability of pulling a number that is in both A and B. So that means that we look at the number of elements that are in both A and B. Well, there are none. A and B do not overlap. So that's 0 in the numerator, still 10 in the denominator. And 0 divided by 10 is 0. So there is no probability of pulling a number out of the numbers from 1 to 10 and getting one that is in both A and B. Now we want the probability of C minus A. So that's the probability of, let's say, we're trying to pull an element out of our universe, and we want it to be in C, but not in A. So the number of elements that are in C minus A is 2. The element 1 and the element 8 are in C, but not in A. All of the other elements of C are in A. And the number of elements in the universe is 10, so 2/10 or 1/5 is the probability of C minus A. And now, these three are the probability of D given B, or C given A and A given C, are the last three problems. This is probably the stranger idea to think of. What we want is, it's the probability of someone pulled one element out of our universe, looked at it and said, by the way, this element is in, For example, in problem 5, this element is in B. Now you tell me what the probability of it being in D is. So basically, problem 5 is the probability of I have these marbles labeled 1 to 10. I pull out a marble, and without showing it to you, I say, by the way, it is a 1, 3, 5, 6, or 10. What's the probability of it being a 6? Well, 6 is one number. There are 5 other numbers that I said it could be, so the probability is going to be 1/5. And this is the formula for how to do this. So the probability of D given B is the probability of D intersect B, which is 1. There's one element that is in both D and B, divided by the number of elements in B. So there are 5 elements in B. So the probability is 1/5. Same thing for problem 6. Formulaically, problem 6 looks like this. And I missed a parenthesis, and I apologize for that. It's going to be the number of elements in A and C, or A intersect C, divided by the number of elements in A. So, what elements are in both A and C? 2, 4, 7, and 9. So there are 4 elements that go on the top of the fraction. How many elements in the bottom of the fraction? Well, 4, because there are 4 elements in A. So the probability of C given A is 1. And that makes sense. We already know that all the elements of A are in C. So if I pull out a marble from my bag and say, hey, by the way, this marble is in A, what's the chance of it being in C? Well, we know because we already showed that A is a subset of C. So every element of A is in C, so if my marble's in A, my marble is also in C. The last problem is the probability of A given C. This is the other way around. I pull a marble out of the bag and I say, by the way, this marble is in C. You have to tell me what the probability of it being in A also is. So the number of elements that are in both A and C are 4. That's the numerator of our fraction. The number of elements that are in A is 6. Sorry. The number of elements that are in C is 6. That's the denominator of our fraction. So the number of elements, the probability of an element being in being in A, given that it is already in C, is 2/3. So here are our answers for these problems. And thank you for watching. I hope you're enjoying learning finite math. And if you have any questions, please email them to my email address. And check out our website and our Facebook page. So have a great day. Bye.